What questions do you have? Things going all right? Yeah. Well, let's continue on with our discussion of linear transformations. Remember again, we have two, pardon me, we have a function that goes from one vector space to another. That's the same as last time. Just put it out there in case somebody hadn't picked one up last time. What makes a function from one vector space to another a linear transformation? What two properties have to be true? So not quite closed, but what do you need instead? So if I do the transformation of a sum. Well, it certainly is in W, because that's just the definition of a function. But what has to be true about the transformation with respect to the sum? It breaks up over addition. And if you've got a constant on the inside, a scalar on the inside, what can you do with it? Bring it out in front. Good. All right. All right. So looking at these properties that we have for linear transformations, looking at this next set of examples for linear transformations for properties, we've got actually a couple of different ways we could prove this particular property. But let's look at the transformation maps 0 to 0. Okay. So let's start with the left-hand side. We talked about this right at the end of class last time. What can I do with that 0 vector on the inside to help us get started here? Yeah, do a 0 plus 0. Because what does that now allow us to do on the right-hand side? Yeah, break it up over the addition, right? And now to get the result, what do we need to do? Yeah, add the inverse to both sides. Good. Because I know that whatever t of 0 is, I know that I can add the inverse of. I know it's a vector in W, so it has the additive inverse, so I can add the inverse of it to both sides. I'll write this out longhand. The reason why we added the inverse is because on the left-hand side now we have what? The 0 vector. On the right-hand side, I need to do something before I get to the 0 vector. What do we need to do? Reassociate. Good. Because now, in these parentheses here, what do we get? 0. Yeah, good. So to finish this off then, I would have 0 equals t of 0 plus the 0 vector, or I just get 0 equals t of 0. We've done that type of proof before, right? This is exactly like the type of proof we've done to show that anything times a 0 vector is 0, for example, or any 0 times any vector is also 0. We've done that same kind of proof. Yeah.
So when you distribute it over the zero, how do you get to the first step? You put the negative
From here to here, I just add. I know that this is a vector in W, so it has an additive inverse. So I just added the inverse of that vector. Yeah, I just added it to both sides. That's what I have here. It's basically like you're subtracting it off. Yeah. But again, this is a very familiar type of proof that we've done before, right? Okay. How about this next one? If I want to show that the transformation of the additive inverse of V really is the additive inverse of the transformation applied to V. Again, same kind of idea here, using a different property this time, or actually we could use the same property again, but let's use a different property this time. how could I rewrite the additive inverse of v using a scalar multiplication? Yeah, negative. Ooh, hey, that was fun. I can do a negative 1 times the v, right? We already know that the scalar negative 1 times the vector v is the additive inverse of v, right? And then what can you do with the scalar? Bring it out in front. And then using the same property, I know that negative 1 times the vector is the additive inverse of the vector. Right? Okay. It's not the only way to get at it, but that was probably the easier way to get at it. That part okay? The next one is similar because how do you define subtraction? Really, subtraction means what? Add the negative, right? It means add the inverse, doesn't it? Right? Now, using a property of the transformation, what can you do with the transformation with respect to the sum? Yeah, break it up over the sum. Yep. So I can rewrite that as the transformation of u plus the transformation applied to the opposite or the additive inverse of v. But what did we just prove in the previous part? That is the additive inverse of the transformation, right? And then by definition, that is the subtraction. This is just playing around with the properties. These would be types of proofs that you should be able to do on the next exam, right? This is a week from Friday, right? Just to remind. Okay. All right. All right. Let's look at this last one. This last one's important because it's going to lead into the stuff that we're going to do in the next couple of sections, actually. If I have our vector v as a linear combination of the v1, the v2, and the vn, then I can applying the transformation to v is also just a linear combination of the transformation applied to each of the v sub i's. Okay. So in particular, if you know what the linear transformation does to each of those pieces, then I know what the linear transformation does to v, is what this basically says, right? What type of a thing do we have for a vector space that we use to write everything in the vector space as a linear combination of those vectors? So span, or in particular a basis, if we want to do it as a uniquely, right? If I have a spanning set, then I know that any vector in my vector space can be written as a linear combination. So basically what this tells me is that if I have a spanning set and I know what the transformation does to the spanning set, then I know what the transformation does, period. Okay. So we're going to be focusing on the transformation on a basis here in a little bit. Okay. All right. In any event, this is not too bad to prove, because if I have my v as a linear combination, what can we do first? Yeah, basically break it up over the sum, right? Oops. Forgot my v1 in there. Repeated use of the first property of linear transformations allows me to break up the transformation over the sum. Then what can we do? Yeah, bring the constants in front. And then we're done. So again here, this is just what the precursor to this is that if we have a basis, is where we're really going here. If I have a basis, then I know that everything in my vector space can be written as a linear combination of the vectors in my basis. So if I know what the transformation does simply to the basis vectors, then I know what the transformation does. That's what this says. Okay. The idea here is what we're going to do is we're going to convert everything back to matrices, which is a huge surprise since that's what we've done pretty much all semester. Okay. All right. Any questions on any of those properties at all? All right. So, like I said, precursor to what we're going to do. If I know that we have a linear transformation, just what we talked about, if I have a basis, how do I know I can write this x? A linear combination, right? If I have a basis and something is in my vector space, then I know that I can write my x as a linear combination of those vectors, right? And if I have a basis, how many ways can I do that? Just one, right? It's unique, right? Good. Okay. I can write x as a linear combination, as a unique linear combination of the basis vectors, which tells me what then, by what we just proved? What's t of x going to equal them? Good. And C2, t of V2, all the way out to Cn, t of Vn. Okay. So let's see if we can apply that to this next problem. Pardon me. I've got V1 and V2 are vectors in R2. I've got the outputs of V1 and V2. Those are vectors in R3. So my transformation here is going from R2 to R3. All right. My input vectors have two components. My output vectors have three. All right. So it's going from R2 to R3. Okay. It says, well, first it says find t of xy. I'm not going to do that. And then figure out what the t of 2, -3 is. All right. So let's see if we can figure out the whole thing first. Because if I can figure out the whole thing, then I can just plug in the 2 for the x and the -3 for the y, right? You agree? Okay. Pardon me. All right. So the first thing I would need to do is, well, let's first check that this really is a basis for R2. Let's ask that first. Does this form a vector a basis for R2? Does it have the right number of vectors in it to start with? Yeah, because any basis of R2 is going to have 2 vectors, right? So it has the right number of vectors, okay? So the only other thing I really need to check is if it's linearly independent. For a set of 2 vectors, how can we check linearly independent easily? Yeah, if there's a scalar multiple or not, right? So let's go this way. What would I need to multiply 1 by to give me -2? -2, does -2 times 3 give me a 1? No. So they are linearly independent because they're not scalar multiples of each other, right? So the answer to this question is yes. Cool. All right. Okay. Yep. All right. So this is a basis. So if I have any vector x, y, whatever that happens to be, we should be able to find scalars C1 and C2 that give me that xy in general, right? We agree with that? Doesn't matter what the vector is. If I know what x is and I know what y is, I should be able to find those scalars. Okay? So can you give me a couple of equations that would have to be true in this case?
-2C1 plus C2 equals X.
Okay. That was just equating first components, right? What else would have to be true?
C1 plus 3C2 equals Y.
Good. Yeah. Okay. Now this is, again, we're trying to find the C1 and C2 given the X and the Y, right? We should be able to do that by setting up an augmented matrix. And row reducing. If you'd use something like GeoGebra or you have a computer algebra system, I could just let GeoGebra do it. It's a little harder to let your calculators do it because those aren't numbers that are given to me, right? So in this case, I'll do it by hand. Won't take us too long. Let's swap row 1 and row 2 to put a 1 in the upper left-hand corner. Yes.
What was it like when you first checked it? Right now, I'm going to checking if the Olympics spots.
I was checking if it was linearly independent. And it has the right size. So if it's linearly independent, then it also spans. All right. What do I need to do next if I row reduce? What do I want to do next?
2 times row 1 and add.
Good. 2 times row 1 and add down. That'll give me a 0 there. 2 times 3 is 6 plus 1 gives me 7. 2 times y plus x will give me an x plus 2y. Right? Next thing we need to do is a 1 where the 7 is. So I'll have to divide everything by 7. So I'll get a 1/7 x and a 2/7 y. Last thing we need to do is multiply the second row by -3 and add up. If I multiply by -3, I'll get a -3/7 x here. Right? Yeah. Okay. Pardon me. -3/7 x. And if I multiply here by -3, I'll get a -6/7, but I got to add 1, so I'll get a plus 1/7 y. All right, so what did we find here? What do those numbers represent? Or those expressions represent? Yeah, the generic C1 and C2, right? So for any xy, whatever the xy is, I know that the C1 is -3/7 x plus 1/7 y times the V1, which was what, -2,1? Is that right?
Does doing the row swap change that?
No. Nope. No, this is still C1 and C2. The row swap didn't change that at all. Okay. That was the vector -2,1, right? And the next one's 1,3. Is that right? So then it'll be plus 1/7 x plus 2/7 y times 1,3. I remember the numbers right. Okay. All right, why does that help? Doesn't look like it helps necessarily, right? But why does that help us? Remember, the problems ask you to figure out what's t of xy, right? Okay. Using what we just talked about with the properties of the transformations, I have my xy here now as a linear combination of these two vectors. So how can I rewrite transformation of xy to start with? Remember, again, these are just constants, right? These are scalars. Okay, so what can we do? I can bring it out. And then it'll be the transformation applied to the vector t negative 2, 1. And bring out the scalar and apply the transformation to 1, 3. Okay. Do I know the answers to those two transformation values? Yeah, what is t of negative 2, 1? Okay. And the other one's going to be 0, negative 3, 5. And then we can simplify, right? What do we get? Oops, I forgot my x. I've got negative 1 times the negative 3/7, so that'll give me a 3/7 x. Notice that my first component and the other one's a 0, isn't it? Okay. And then negative 1 times that'll give me a minus 1/7 y. What about the second component? Well, 2 times negative 3/7 is negative 6/7. And then I'll get a negative 3/7 when I do the second one. So I'll get a negative 9/7 x. 2 times 1/7 is 2/7 minus 6/7. So I'll get a negative 4/7 y in the second component. This one's going to give me a 0 in the third component. So I just need to worry about the third component here. We'll get a 5/7 x plus a 10/7 y. I'm just distributing and adding, right? I did it all at once. Do we see where they're coming from? The second component is the more confusing one because I got two things going on, right? I just was doing my x's and then my y's. 2 times negative 3/7 plus negative 3 times 1/7. That's my x, right? 2 times 1/7 minus 3 times 2/7. That's my y. Just combining. Assuming I did that arithmetic correctly. All right. So that is the answer to what's the transformation applied to xy. Yes. I have 1, 2, 3 components. I did do the 5. 5 times 1 is 1/7 is 5/7. 5 times 2/7 is 10/7. I did do the 5. Okay. The problem asks you for t of what? 2, negative 3. So now we just need to plug those in. So you'd have 3/7 times 2 minus 1/7 times negative 3. Negative 9/7 times 2 minus 4/7 times negative 3. 5/7 times 2 plus 10/7 times negative 3. What is that? 13/7 in the first component. Negative 18 plus 12 is negative 6/7. 10 minus 30 is negative 27. Once I found the transformation, at that point I can just plug the numbers in. And that's the whole point of this. If I know what the transformation does to a basis, right? If I know what the transformation does to basis vectors, I know what the transformation does, period. Right? We did all the hard work by finding the formula. Once I found the formula, I can just start plugging the numbers in. Okay. So once we know what the transformation does to the basis, I know what the transformation does, period. Okay? That's what that says. Let's see if we can do the next one. Okay. In this case, let's not worry about finding the rule because that takes us a little bit longer since we had to row reduce. Let's just worry about this one so we can actually use our calculator. Okay? Make it a little bit faster. Okay? First off, what's your domain space and what's your codomain space here? Where are your input vectors coming from? R3? And where do they end up? R2. Good. Right? Yep, that's it. That's because that's where these things are going in. Yep. Okay. So the first thing I need to do is ask the question: is the set 1, 2, 1, 2, 9, 0, 3, 3, 4 a basis for R3? That's the first thing we need, right? If I'm going to use this to figure out what the transformation does, I need it to be a basis, right? Okay. How would you check that this is a basis? What do we do? It needs to be linearly in spans. How do we do that? Yeah, make a matrix and row reduce. So we'll make those as columns of a matrix. And unless I'm an idiot when I made the problem, you should get that. I am not ruling out that I was an idiot. Just saying. Otherwise, this would be a terrible example. Okay. All right. So it is a basis. So the answer to that question is yes. It's a good review, right? We've done this stuff before, and the final's coming up. Yeah. Well, I don't have to make it a basis. If I'm going to do the first part, then it better be a basis, right? Because I need to be able to write every single vector in R3 in terms of those three. I don't necessarily need a basis for the last part, as long as that vector is in the span of those three. Yes.
So for also to
Say it again. For the two, yeah, for R2 you could use a matrix. Yep. All right. So what I need to do next, I know what the transformation does to the three basis vectors. So what do I need to do with this vector here that I'm circling, the 7, 13, 7, relative to the basis? What do we need to find? Yeah, I need to find the coordinates relative to that basis, right? I need to solve that system. So I need to take that, pardon me, vector and augment it and row reduce. Because again, I need to know what constant times the first vector plus what constant times the second vector plus what constant times the third vector gives me the vector that I'm interested in, right? Sorry, Declan. I stepped on your scooter. What did you get when you augment that, or sorry, row reduce that? Good. Everybody know why we did that? Trying to find those constants that the negative 1 times v1 plus v2 plus 2v3 gives me the vector. All right, so how can I write the transformation applied to 7, 13, 7? What's that going to equal? Well, that is yeah, so it'll be the negative 1 times the transformation applied to v1, right? Plus the transformation applied to v2 plus 2 times the transformation applied to v3, right? We agree? And I know those answers. They give us those outputs, don't they? Negative 1 plus negative 1 plus 2 gives me 0. Negative 0 plus 1 plus 2 gives me 3 on the end. When I add? Oh, it's 2, 0. Jeez. Thanks. Yeah, 2 times 0 is 0. Last time I checked. Thank you. The process okay?
So we could do the same thing for the problem before.
We,
We need to use X and Y.
the problem asked us to find the rule, so I did the rule first. But in this case, you wouldn't have had. You're right. In the problem before, you wouldn't have had to find the rule. You could have just done the one step for that one. But then if you had a different vector, you'd have to do it again. And then if you had another vector, you'd have to do it again. Which is why we just did it in general first. Yeah.
So, like, would you want us to find the rule first and then plug it in? Or
I wouldn't. If I wanted you to find the rule for something that large, I would probably have you use GeoGebra or something, so you wouldn't have to do it all by hand. Because again, with all the fractions that you might be getting, the work could be messy. Yeah.
so in the X and Y, that's the previous question.
The previous question would be okay because it's not that bad, right? It was just a 2x2. I wouldn't ask you to do a 3x3 on the test. That would just take too long. But you should understand how to do it. Okay. All right. So our goal here is to try to, at least in this case, replace what's going on with matrix multiplication. So let's see what happens here. All right. So let's look at the couple of examples that we have here. In this case, we've got a transformation going from what to what. What's your input space and what's your output space? Yeah, it's 2 to 3, right? R2 to R3, right? Let's first just apply the transformation to the basis vectors, standard basis vectors. Standard basis for R2 is 1, 0, and 0, 1, right? Yep. What do you get when you apply the transformation to 1, 0? Well, the 1's going in for the x, and so it's 0, 3, 1, right? The 1 goes in for the x, the 0 goes in for the y. Yeah. What do you get for the next one? Good. Okay. Why did I use the standard basis? Well, I can get the coordinates easier, right? I know that I have it written slightly differently here. I already know what the transformation does. But I also now know that my transformation applied to xy is going to be x times the transformation applied to 1, 0 plus y times the transformation applied to 0, 1, right? We agree? Well, I know what the coordinates of x, y are with respect to the standard basis. The x coordinate is x, the y coordinate is y. So I'm just writing it as that linear combination, right? We agree? Okay. Let me start writing things as column vectors here a little bit. My transformation applied to 1, 0 is the vector 0, 3, 1, right? We agree with that? Okay. And my transformation applied to 0, 1 is y times, just the 0, 1 is negative 2, 0, 2. Yeah. Okay. Can I realize this now as matrix multiplication? This is where we're trying to head to, by the way. Oops. Well, if I think about what I get out of this, this is a 3 by 1, right? Notice that if I take a 3 by 2, which would be this matrix, and multiply it by a 2 by 1, I get a 3 by 1, don't I? And I get the same thing, don't I? I'll get negative 2y for the first component. I'll get 3x for the second component. I get 1x plus 2y, right? Where am I still going?
In the Y column, the last.
Oh, it's a negative 2. Sorry. Yep. There we go. Now I get the same thing. Okay. Yes. That's the standard basis for R2, 1, 0, and 0, 1. Yeah, that's the standard basis. Yep. Okay. Do you recognize any relation between this matrix and this transformation we started with? These are the x coefficients, aren't they? These are the y coefficients, aren't they? Okay. So this is exactly how we form what we refer to as the standard matrix for the transformation. One of the notations for that is just to put brackets around the t. So the standard matrix here is 0, 3, 1, negative 2, 0, negative 2. Notice that, again, we went from R2 to R3. What size matrix did we get? 3 by 2. Notice it kind of flip-flops the dimensions, right? Okay. The number of rows is the dimension of your output space, the dimension of your codomain. The number of columns is the dimension of the domain. Okay. So let's look at the next example here, and let's see if we can figure out what size matrix we should have and what the columns are going to be. Now notice again, how did I get 0, 3, 1? That was applying the transformation to 1, 0, right? And this was applying the transformation to 0, 1. These are just the columns when we apply to the standard basis. All right, let's look at the next one. What are your dimensions of your domain and codomain? 4 and 3. Good. So your matrix is going from R4. Sorry, your transformation is going from R4 to R3. So what size matrix should we have? 3 by 4. All right. What's going to go in the first column? Those are your coefficients for the x1, right? Why are those the coefficients for the x1? Because the numbers here come from applying the transformation to the standard basis. The first element in our standard basis is 1, 0, 0, 0, right? So it'll kill off the x2, the x3, and the x4. What do you get in the next column? 2, 1, 0, right? Because you're going to put in 0, 1, 0, 0, right? What do you get for the next column? 1, 1, 0. Those are the coefficients on the x3. And what do you get for the last column? 1, 0, 0. So this is your standard matrix for that transformation. That's the answer. This one's just asking us for the matrix, yeah. That's the answer.
Oh, okay.
And then notice that you can realize the transformation now as matrix multiplication, right? Because your input space would have x1, I'm just writing it next to it. You don't have to write it down. x4. What happens when you multiply? Your first component is going to be that row times that column. Don't I get exactly that when I do that? Right? The second one's going to be that row times that column. Again, I get that one. Okay? So the idea here is to replace the transformation with matrix multiplication. Okay? All right. Let's look at the next one. This one, notice that it's describing it to you, and you might want to find what the matrix is. Projection onto the y-axis. That's a different thing. Okay? I don't know why I said y-axis. I should have changed that to the xy plane. Okay, let's make it xy plane. All right, so What that means is that if I have some point here, x comma y comma z, I'm going to drop it straight down. What should be the coordinates of that point for the output? It should be x, y, 0, right? So that's why I can think about it going to R2. So I can think about my transformation of x, y, z just being x comma y. It's just killing off the z component. Okay? That's the idea. Okay? All right. So what would your matrix be here then? What size would your matrix have? Start there. 2 by 3. What's your first column going to be? It's a 2 by 3. So it's going to be 1, 0, right? What's the next column going to be? 0, 1. And the last column will be 0, 0, right? Because remember, again, these are the images of your standard basis. What's your standard basis for R3? One zero 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 one zero 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 one, right? When I put in 1 0 0, what vector do I get out? 1 0. When I put in 0 1 0, what vector do I get out? 0 1. When I put in 0 0 1, what vector do I get out? 0 0. Right? Okay. All right. So there's our matrix for that one. Let's do the next one. Reflection about the line y equals x, or negative x. So if I start with some arbitrary point x, y, and I reflect, about the line x equals y equals negative. Try that again. Y equals negative x. What happens? So, okay, so maybe I probably didn't draw that particularly well. I agree with the negatives, right? Because we're flipping them around. Yeah. So if you had one over here, gotta be a little bit careful, right? Because that would be the reflection there, isn't it? It's not quite. So in this case, if you had your x was negative, it's still negative, isn't it? Okay. What's happening with your coordinates, do you think? Okay, so yeah, there should be some y and x's flipping around, right? Okay. Should be a little bit careful. Is it negative y, negative x though? If I'm up here, part of my problem. Let's do some specific numbers here. Let's say we had the point -2, 1. Where would that end up? So this is -2, 1. This is -1, 2. That looks like negative y, negative x, doesn't it? With negated the y, negated the x. Yeah. So I think this might be the right transformation. So let's go with that. Okay. So what's your matrix gonna? What size is your matrix gonna be? It'll be a 2 by 2. What's your first column gonna be? 0, negative 1, right? Because again, you would put in 1, 0, and you get out 0, negative 1, don't you? What do you get for the other one? Negative 1, 0. That would be your standard base or standard matrix for that one. Questions on that? Okay. If you want to start just a little bit in the next section here, finish it up on Monday. Remember, we don't have class on Friday for celebration of scholarship. So the next one here, we're going to talk a little bit about some different properties of linear transformations. In particular, we're going to refer to what we call the kernel of a transformation, and then the range of a transformation. Range is something you should be familiar with. Kernel is probably a word you haven't heard, at least not in the context of functions. Kernel, you may be thinking of, Kentucky Fried Chicken, perhaps. All right. A little bit of popcorn. Yeah, exactly. All right. So what do we mean by the kernel? Well, the kernel is, we denoted it with KER of T. The kernel is the set of all vectors in your domain that get mapped to the 0 vector in the codomain. What's one element, what's one vector that always has to be in the kernel by something else that we proved today? The 0 vector is always in there, right? So note the 0 vector is always in the kernel, no matter what. Okay? The range, which we denote RAN of T, this is everything in your codomain that is the output of something. Okay. It's everything in the codomain that is mapped to something here, right? That is mapped by mapped to, or something in the domain gets mapped to that element. That's what we mean by a range. Set of all possible outputs. As you may guess, these turn out to be subspaces. Let's do the first one. Okay. What do we need to do? There's a couple of steps that we need to do to show that something is a subspace. What are they? Closed under addition, closed under scale under multiplication. We also need to make sure that we have a non-empty set. But why do we know that the kernel of T is not empty? Yeah, the 0 vector is in there, right? So the kernel of this is not the empty set, since we know that the 0 vector is definitely in there, right? So let's start with 2 vectors in the kernel. How do you get in the kernel? Good. The transformation is equal to 0. We need to show that it's closed under addition. So we need to show that V plus W is back in the kernel. How do I show that something is in the kernel? What does it mean to be in the kernel? Good, yeah, the transformation of it gives me 0 out, right? So if I take the transformation of the sum, what can I do with that? Break it up, good. What do each of those equal? 0, because both of those elements are both of those vectors are in the kernel, and then the 0 vector, it plus itself is the 0 vector. So the sum of the 2 vectors is back in the kernel. We also need to show that it's closed under scalar multiplication. That means we need to apply the transformation to a scalar times one of the vectors, right? So for the second part, Apply the transformation to the constant times the vector. What can we do with the constant? Bring it out front. The transformation applied to v is equal to 0. And anything times the 0 vector is 0. So the scalar multiple is back in there again. So we showed that it was a subspace. Okay. We'll show that the range is a subspace next time. I do want to give you some homework problems here in case you want to work on them. It says it's due Friday, April 30th. Well, April 30th isn't a Friday. So, anyway, that'll be good practice problem for the exam anyway. We haven't done all of it yet. We'll do more of this next week. I'll go ahead and hand it out now. All right, so we'll work more on kernel and range next time. We'll also do matrices of general transformations next time. And we can also talk about how the matrix will help us. All right, have a good one. Remember, no class Friday for celebration of scholarship. Uh-oh. Whoops. Our math and CS presentations are at 9. Start at 9 o'clock on Friday. 9 to 11. We'll have bagels, coffee, all that good stuff. I encourage you to come see they'll be in the UC 138 and 142. Have a good one.